So I'm going to talk a little bit about the SIR model and the concept of herd immunity. So first of all, what is the SIR model? So the SIR model is this little model to study infectious diseases. It's sort of the base case, classical, most simplest version of a model that you can think of. And in this SIR model, we divide things into three buckets. So there's going to be the susceptible population that's going to basically start off at the entire population. There's going to be the infected population. So these are the people that are currently infected. And then there's going to be the population that was infected that then recovered. Now, we're going to think of everything as the share of the population because it's going to make the mathematics a lot easier. So if you're just thinking of a population with millions of people, we can just think in terms of share, and then we can multiply up to get what the numbers, the total numbers of susceptible people, infected people, and recovered population is. So it's going to be the case that basically the sum of these shares add to 1. We're also going to be using this other concept, which is what's the share of the population that isn't susceptible, okay? And it's going to be the sum of infected and the people that have recovered. So by assumption, in the basic SIR model, we assume that people that are infected and recover, they can't become reinfected. So that's going to be a critical assumption. Now, let me just say, before I get into this, that I'm going to use a quote from George Box. All models are wrong, but some are useful. So this SIR model is not a panacea, but we can learn some basic insights from simple models like the SIR model. Experts in the field that are studying the infection use much more complicated models, and as we're going to see that these models are, contain in some cases some important non-linearities, and so they need to be solved with special techniques on computers and so on. Learning the basic SIR model and some key concepts, I think, are going to be useful in engaging in discussions with experts that, again, use these more complicated models to analyze the data and to make predictions. And the advantage of this simple SIR model is that it's going to allow us to think about important concepts such as the famous R0 variable in the literature, which I'm going to spend a lot of time in my discussion on, as well as this concept called the herd immunity threshold. Okay, now I'm going to give you a big warning in advance that this literature has too many R's in it, and I'm going to explain by what I mean by that. That's one of the reasons why it's a little confusing to read different strands of this literature. I'm going to try and kind of to tie things together a little bit. Okay, so what is R0? So this is the famous R0 that probably you read about in newspapers or on the internet. And so R0 is the number of new infections that are generated by the first infectious individual in a completely susceptible population. So this is the very first person that starts things off. And so this R0 variable, and the reason why it's called R0, is we're going to think of time beginning in period 0. Okay, so R in period 0, which we refer to as R naught, is going to be equal to some number. Okay, so just for illustrative purposes, I'm going to use the number 5 in my example. So just to warn you, an R naught equal to 5 is like a really big number. Okay, so the estimates are that for COVID-19, R naught is probably lower than that. But just for the sake of my numerical example, it makes things easier. And so right at the very beginning, where the size of the susceptible population is basically 1, in other words, it represents the entire population because it's assumed to be 1 in this case. If R naught is 5, that means that the first person, which I'm going to characterize by this red dot in the slide, and the black dots are going to be the susceptible people in the population. So we're going to assume that this red dot, or this first person, comes in contact with 5 susceptible people, which are going to be, again, these black dots. And so we're going to assume with R naught equal to 5 that this first person infects 5 people. So that seems like it's under control at this point. But the problem is that early on in the process, where the population is very, very susceptible, there's a large, almost the entire population susceptible. Those 5 people are going to then infect 5 other people each. And so it starts off at 1, and then it infects 5 people, and then the 5 people each infect 5 people. So there's now 25 people that are infected. If the 25 people each infect 5 people, then it's 125. Well, you keep on going, and once we get up to the 10th solution, we have like 10 million people. It's like an absolutely gigantic number. So obviously, if this was like a big city, we'd start running out of people to infect. Okay, so just to give you an idea that an R naught equal to 5 is like a really big number. Now, we have another R. So we had R naught, which is the very beginning of the process, when the proportion of the population is mainly susceptible people, entirely susceptible people at the very, very beginning. Now we have another concept, which is the effective reproduction number. And it's going to be equal to R naught times the proportion of susceptible people in the population. And so just to give you an example, so we have an equation at the bottom that says that the effective production rate, RET, is going to be equal to R naught times this S variable, which is going to be the proportion of susceptible people. So if R naught was 5 again, and the proportion of the susceptible people had fallen from 1 down to 0.2, in this case, then we'd have the 5 times the 0.2. And so the effective rate of production, once the susceptible population had fallen from 1 to 0.2, this effective reproduction number would be 1. Now it turns out 1 is like a very special number, because if we think about this on the, back to the green dots and the black dots, in this case, the red dot, when the susceptible population is like 20% of the population, or 0.2, he's still going to be running into 5 people, but 4 of those people, the green dots, are no longer going to be susceptible in the population because they've already been infected or they've already been recovered from the infection. And so despite the fact that he runs into 5 people, he's only going to affect 1 of those 5 people. okay? And so when we think about this process around the point where the effective reproduction number is around 1, we're going to be observing one person infecting one person. And of course, if the first person recovers and the second person infects another person, the disease will no longer be growing at a very, very high rate. And even at that point, when 20% of the population is susceptible, as we think about people infecting other people, the proportion of the susceptible population is going to be declining from 20% gradually until you entirely run out of people to infect. And so that's going to be where things go in the very long run. So the effective reproduction number, again, RET, is going to be equal to this R naught, the 5 in my example. But the proportion of susceptible population in the very, very long run is going to be 0. And so what this means graphically is that the red dot is going to be running into people, and because they've all been infected and recovered, the effective reproduction rate is going to be 0. So you might say, well, that's kind of a ridiculous example, but it's trying to show that in between the point where this effective reproduction rate is 1, as the proportion of the susceptible population continues to decline from 0.2 to 0, this effective reproduction rate is also going to be declining after it reaches 1. Okay, so that sort of explains the intuition. I'm going to go later into the mathematics and then prove this for those people that can last that long. So the very first thing is this concept of what we call the herd immunity threshold, okay? And this is probably the most important use of this R naught concept because it determines what proportion of the population needs to be immunized through vaccination to eradicate the disease, okay? So generally, the larger R naught, the more difficult it is to control the disease. So for simple models like what I'm going to be working through, the proportion of the population that needs to be immunized, in other words, to not be susceptible, to prevent the spread of is going to be this following equation. So it's going to be Q, which is going to be equal to 1 minus 1 over this R naught. And so if we work through an example, so for example, suppose that R naught was 5, which is the example that I was using before. So we work out the formula. So Q is going to be 1 minus 1 over 5. And so that's going to be 1 minus 0.2 or 0.8. And so with an R naught of 5, we would have to have 80% of the population that would need to be vaccinated to achieve this herd immunity. And what we mean by that is that once you reach this herd immunity, there might be some local outbreaks of the infection, but you're not going to observe what we refer to as exponential growth, because effectively you've run out of most of the population to infect. And that's going to contain what the ability of the infection has to grow, because its population that it's trying to infect is actually falling. So these are some estimates of the R naught values. So just to put this into perspective, remember I was assuming like R naught, again, this is the basic reproduction number. So I was assuming a number like 5. And so that would be the case of the lower bound estimates of smallpox and polio. Okay, so if we look at the 5 to 7 range for those infectious diseases, you can see that the herd immunity threshold on the right-hand side is 80% at the lower bound when it's 5, and 86% on in terms of the upper bound. Okay, and you can see for something like measles, that has an R naught that's a lot larger, like 12 at the lower range. The herd immunity threshold can be as high as like 92%. But if you're talking about influenza, which is at the bottom of the table, that only has an R naught of around 1.5 in the lower range, then you reach herd immunity at 33% of the population. Okay, so that's the bottom line. That's the equation that's used where this herd immunity threshold is basically a function of this R naught thing. And so now what I'm going to do is to get into the details of the SIR model. So again, S stands for the bucket, or the compartment of the susceptible population. And we're going to think of this again as the share, not the level of susceptible people. And then you can go in the susceptible population to be infected. And so that's the downward arrow to this IT variable, which is going to be the share of the population that is currently infected. And then there's going to be a proportion of the population that recovers. And so this is going to be the R variable. And this is where we have problems with the notation in this literature, in the sense that I've already used R twice. I have an RE, which is the effective rate of reproduction, and the R naught. So these variables are not to be confused with the R in these SIR models. Okay, so now unfortunately they're very much connected in terms of this literature, but unfortunately the notation is a little problematic. Okay, but now you have to keep track of this R, which is the proportion of the population that is recovered after they've been infected. Now, a critical assumption is that these recovered people, they can no longer ever get the disease, so they can't go back to the susceptible category. Okay, so this is just the warning about notation, which makes this literature maybe more difficult to follow than what it should be. Okay, so let's go back to the model. And so we're going to start to define some characteristics of the model. And one characteristics of the model are the initial conditions, or where the 3 variables S, I, and R, where do they start in period 0? So again, this is the very beginning of the pandemic. And so S in period 0, which we're going to characterize as S in parentheses 0, is going to be equal to S naught. And this number is going to be approximately 1. Okay, and the reason is that at the very beginning, there's only going to be one person that's infected. And so you can think of this as the one person over the total population. Okay, so it's going to be a very, very, very small number if the population is, say, a city or a country, or so I0 is going to be equal to I naught, and this is going to be the share of the infected population again. And in this case, it's just going to be that first person divided by the total population. And of course, R naught, not to be confused with the other R naught, is going to be equal to 0 because in period 0, there hasn't been anybody infected in the past, so there's nobody to be in the recovered state and so on. Okay, so those are the initial conditions in the model. And again, because SI and R are shares of the population, they will sum to 1. Okay. Now, the equations of the classical SIR model have 3 differential equations. So I'm going to be using what we call the continuous time representation of the model. You can find discrete representations on the computer, and we've coded up discrete representations to be able to study this model as well as somewhat more complicated versions of the model where some of the parameters are, for example, time varying. So what I'm going to do is go through these 3 differential equations piece by piece. So the very first one, in some sense, the most important one, so all of them are kind of equally important, but in terms of understanding actually what's going on, the most interesting one, which is also the most complicated one, is the second one. So this is the equation that describes the evolution, or in this case, the time derivative of infections. And so that's what we mean by DI dt. So this is the rate of change of the share of the infected population. And we can see that it depends on the interaction between the susceptible population S and the infected population. So you just think that there are these susceptible people and infected people, and the interaction of these 2 things, pardon me, the interaction of these 2 types of people in the population multiplied by a parameter A that's going to determine how infectious the disease is, okay? That will determine how fast this share of the infected population is going to be growing over time or falling, possibly. That's what we're going to see here in a sec. And so that makes sense. That basically it should be a function of the interaction of the susceptible group and the infected group. That is going to be a movement from the susceptible group to this infected group. And so the amount of people that are adding to the infected group are going to be subtracted off the rate of change in the share of the susceptible population. So we see we have a positive ASI in the second equation, and then we have a minus ASI in the first equation. Okay, so as people are being infected, the share of the susceptible population is going to be declining over time. And those people are going to be moving from the susceptible share of the population to the infected share of the population. So the same thing happens, or a similar thing happens. So people get infected, they enter the infected population, and then a certain proportion of them recover. And so that we're going to think of as being minus B, another parameter, times the infected share of the population, okay? And again, because they're going to be moving from the infected population to the recovered population, that's going to enter as a positive B times the infected population in the last equation, which again is the the proportion of the population that is recovered, okay? Now, it's very, very important. So in the basic model, you just recover from this infected population. You know, in the real world, unfortunately, some people don't survive. Some people survive and some people recover and don't survive. So this model basically assumes that the death rate is basically a small number, and it ignores that obviously real world feature, which is obviously built into the more complicated models. Now, back to R naught, like the big R naught, the one that you'll read about in the newspaper, and the one that people use to compare how infectious different kinds of infectious diseases are. In this model, the R naught is going to be A divided by B. So again, A determines the parameter where people are flowing from the susceptible population to the infected population. B is all about how they're moving from the infected population to the recovered population. Now, I don't want you to think of A as being something that's necessarily fixed in my calculations. I'm going to assume that it's fixed, but in the real world, with doing things like social distancing or washing your hands or wearing masks, we can actually influence A, okay? But for the sake of my calculations, I'm going to assume that A is fixed. Now, this is a graphical representation of the three variables in the model. S, the susceptible share of the population, I, the share of the infected population, and R, the share of the recovered population. So if you just look at these graphs, you can see that, again, the share of the susceptible population starts off approximately 1, and then it has only one where to go, and that's to decline towards 0. And you can see that that's what it does. So it declines very slowly at first, and then it starts declining rapidly, and then gradually it goes into 0. The recovered population, of course, starts at 0, and it gradually increases over time until it reaches 1. The infected population is something that starts off at 0, and again, at the very beginning, it's 1. It then starts increasing at an increasing rate, reaches a peak, and then starts to decline. And so that's the equation that's probably most interesting. This is the dI/dt equation, which, remember, is this parameter A times the interaction of the susceptible and infected population minus this parameter B times the infected population. So it's basically the sum of these two other curves, the susceptible curve and recovered curve. So remember, at the very, very beginning, we go back to the red dot and the black dots. So at the very beginning of the process, you have the one red dot infecting 5 people. Remember, the 5 people then infect 5 other people. So it goes from 1 to 5 to 25 to 125. This is referred to as a process that has exponential growth. And so you can see early on, the red line, we have it increasing at an increasing rate, okay? And so this is early on in the process where the share of the susceptible population is really, really high. So I should have told you that the horizontal axis is time, okay? So then we have the point where the red line reaches a maximum. And again, it's going to turn out that this is the point where the effective reproduction rate is 1. So remember, that's the situation where one person, the red dot, still runs into 5 people, but 4 of the people have already been infected or recovered, and as a result, he doesn't infect those people. He only affects 1/5 of those. So again, this is a situation, a very special situation where you're at the peak, where the effective reproduction rate is 1. And so this is going to be the point where it's going to be the maximum value of that curve. And so this is the situation where that time derivative, and this is where the proof is coming in. So the point where that function reaches a maximum, the derivative ASI minus BI is going to be equal to 0. Okay, so before that, it's going to be positive. So this is the upward sloping part of the red curve up until it reaches that maximum value. And then on the other side of it, as time progresses, on the other side of that maximum value, infections are going to be falling over time. Okay, so we can take that equation and we can set it equal to 0, like we've done. And then what we can do is cross out those I, so the infection rate drops out of the equation. And so we get this expression that A times S is minus B is equal to 0. Or another way of putting it is that S is equal to B over A. But remember, R naught is equal to A over B, okay? And so this S value equal to B over A, which is going to be associated with the maximum number of infections in time, is going to be 1 over R naught. Okay, so that's, again, the share of the population that is susceptible is going to be 1 over R naught. Okay, but the herd immunity threshold will be the proportion of the population that is not susceptible, and it's going to be equal to I plus R. Okay, which is equal to 1 minus the proportion of susceptible people. Okay, and so that means this Q value, which is the thing that we were trying to derive, is basically going to be equal to 1 minus S. So this is going to be the 1 minus the share of the susceptible population. It's going to be equal to 1 minus 1 over R naught, which is the equation that we assumed initially. Okay, so that's that's sort of showing how it works in the very, very simplest, simple classical SIR model of infectious diseases. Now let's think about what happens when we have vaccinations. Okay, now we need to adjust the model a little bit. There are 2 additional terms that come into the equation. So remember, before we had Q is equal to 1 minus 1 over R naught. And now we're going to have Q is going to be equal to N minus 1 over R naught plus this 1 over epsilon term. And so the N thing is going to be the proportion of non-immune individuals. Okay, so instead of assuming that that everybody was susceptible at the beginning of this thing, we're going to assume that some people were vaccinated, and so not everybody was susceptible because some of the people were vaccinated. But we're going to assume that the efficacy of these vaccines is not 100%. Okay, so for example, the Pfizer, Moderna, the tests are approximately 90%, 95% efficient. but 5% of the people that get the vaccine might go on and get the disease if they're exposed to it. And the AstraZeneca, the estimates are 70% efficiency. Okay, so that's going to influence this herd immunity calculation. And so just for illustrative purposes, we've chosen a range for R naught between 2.9 and 3.7. So you remember when I was referring to this before, I referred to the number 5, and I tried to tell you that was probably too big. So if you look at the empirical literature, it looks like it's between about 2.9 and 3.7. Well, we can do a simple calculation in the case on the US. So if we thought that 94% of the population is not immune at this point, then N would be 0.94. If we think R naught is somewhere between 2.9 and 3.7, so we can plug that into the 1 over R naught thing. And then we can consider two scenarios, one where we have 70% efficacy or 94% efficacy. So you can see that as we reduce the efficacy of the vaccine, the threshold for herd immunity increases. And in fact, under particular combinations of high R naughts and low vaccine efficacy, the immunization threshold might actually even be greater than 100%. So the bottom line here is we need to find vaccines that have high efficacy. Okay, so that's sort of the basic model, and hopefully that's useful for helping you to think about some of these numbers that are reported in the newspaper or on the news, and so I'd like to just thank you for your attention.